Alright, so this is an example from your book. It is under the section of multi-loop circuit. So we've got an example, and then this example consists of a circuit which has elements of two kinds, resistors and batteries. It's very similar to the way to the question we've seen in recitation. So the very first job here would be to name different points in this circuit. After you've done enough questions, you don't need to do this. But I'm going to go ahead and name these points: A, B, C, D, E, and F. Alright, let's first start with having currents in this circuit, and we'll make sure that every element in this current has some in this circuit has some current. So let's say this down here current is I1, here current is I2, and there's some current I3 here. So this I3 is also in this resistor and also in here. I1 is also here and then here. I2 is here, here, and here. So I'm going to delete all the other arrows for now. Okay, so we have got three currents, I1, I2, and 3, and then we make sure that these currents, like one of these currents at least, is going through at least one of all the elements. Sorry, I said that incorrectly. What I mean is that we'll make sure that every element in this circuit has some current going through it. So we've got I1, I2, and 3. At point C, well, so the step 2 would be to write down Kirchhoff's first law, and that is at point C we will have current coming in will be equal to current going out. That means we have I1 plus I2 equals to I3. Let's call this equation 1. Now look at the loop A, B, C, D, A. Okay, A, B, C, D, A. So from A to B we don't have any element there, but between B and C we have one battery and one resistor of 6.0 ohms. So what I'm doing is I'm going in this direction in this loop, right? This is the direction of travel. That means okay, let me make it such a way that it's more visible what's going on here. Yes, this is the direction of travel in that loop. This is the sense of rotation in that loop. And the very first thing I see is this battery. And using the 4 conventions that we have developed in the past, I'm going to write down this potential to be plus 10 volts. Because I'm moving in the direction, I'm coming in from the direction where the terminal is minus, so my potential difference will be plus 10 volts. Now next I see this resistor 6.0 ohms, and it has current I1 going through it. That means I'm traveling in the direction of the current. That means that it should be minus IR, I1 times 6.0 ohms. Then going here we have got current I3, and we are going in the direction of the current. So I3 is here, that means I3 is also here. So we are going in the direction of this current on going through the resistor with the resistance 2.0. So it's going to be again minus whatever the current is going through that thing times its resistance. So you get your equation number 1. Sorry, equation 2. Now we look at the loop B, E, F, C, B. B, E, F, C, B. For B, E, F, C, B, we are moving like this, right? That's why it's B, E, F, C, B. And the current direction is here it's this, here it's this, and current here is on 6 ohms is here. So the very first thing we see is a resistor of 4.0 ohms between B and E, and I'm traveling in the direction of the current. That means the potential difference will be I2, because that's the current going through this circuit, this branch, this resistor of 4.0 ohms times the resistance. Okay, then I look at this battery, and I'm coming in from the side that is of positive terminal. That means the battery voltage that I will be writing down here will be minus 14.0 volts. So whatever the voltage I'm writing down for each of these elements, I'm using the conventions that I have developed in the past. Then you look at this 6.0 ohm resistor, and right here I'm traveling in the opposite direction of the current. That means I'm going to write it down as plus 6.0 I1. Then I see a battery, 10 volt battery, this one, and I'm going like this. The very first terminal I see is positive. That means I will write down this battery voltage to be minus 10 volts equals to 0 in your equation 3. Okay, you can also write that equation 3 to be minus 24 plus 6.0 I1 minus 4.0 I2. That's equation 3. Now our job is to figure out these currents I1, I2 and I3 using these three equations. So you've got three equations and three unknowns. So if you use substitution, if you multiply some equation with something, add two equations, after doing that you'll get rid of something and then you will be able to solve it. I'm going to go ahead and I do the solution here. So let's copy these equations in the next page. Okay, so we've got these equations. Let's simplify them a little bit. So I don't need this in order to solve it. And let's say these two things are the same, so I'm going to use the equation that's over here. So these are the three equations I have, right? And also this is equal to 0. Okay, so let's solve. Let's do one thing. Okay, let's substitute the value of I3 from equation 1 into 2. So now after you have established these equations, you just have to do mathematics, and that's it, just some algebra. So it's 10 volts minus I2 6.0 minus I3 is I1 plus I2 times 2.0 equals to 0. And let's call this equation 4. Okay, when you solve this equation you'll get, let's not call this 4 just now, when you solve this you'll get 10 minus 8 I1 minus 2 I2 equals to 0. So let's call this equation 4. Now what you do is, so there are multiple ways to solve these kind of problems. So the concept is there are three variables and three unknowns, so you can solve this problem. Now I'm following exactly what is given in the example, so that if you want to look more into, how I'm doing this, you can just read the example. So the next job is to multiply equation 3 by 4 and equation 4 by 3. So if we do that, we get, we are multiplying equation 3 by 4, so I'm going to get 96 volts plus 24 I1 minus 16 I2 equals to 0. And let's call this equation number 5. And the other one, when I multiply equation 4 by 3, I get 30 volts minus 24 I1 minus 6 I2 equals to 0. So it's very clear what I'm doing here. I'm going to add these two equations to get rid of I1. So that's exactly what I do. I add these to get rid of I1 term. So I get, and then I know what these things are. So I can solve for I2, and I2 will be minus 3.0 ampere. Okay, that's your first answer. So now we've got this, right? So we can figure out, look at this equation right here. This one, equation 3. So in this equation, if you know either of I1 or I2, you can find the other one. So I'm going to use this equation. So I just calculated I2, right? So use I2 equals to minus 3.0 in equation number 3 to get I2. And when you do that, you'll get I2 to be equal to, you get to get I1. To get I1 you will get to be 2.0 ampere. And also using equation 1, we know that I1 plus I2 equals to I3. This implies that if you use I1 and I2 values, you get I3 to be equals to minus 1.0 ampere. Now let's do one thing. Let's copy these values. So these are your final answers, okay? Now let's interpret the signs. Let's copy this to here. Okay, let's have them closer. Okay, so this is what we have. We've got I1, I2 and I3. So we started with assuming these directions of these currents, right? So because I1 is positive, that means the direction of the current that we chose at the beginning arbitrarily was correct. That means I1 is really in this direction. I2 on the other hand came out to be negative. That means I2 in the real world is in this direction. Okay. Same with I3 came out to be negative. That means the direction that we chose was opposite of what it is really. So I3 in the real world is like this. So if you do, so that's why we start with choosing the direction arbitrarily. Is the signs in the end that tell us what the directions of the currents are actually.